And our main presentation today, our speaker is FBAC member James Wooten. He's been a long FBAC member. He also is known for the Houston Museum of Natural Science. There are people known for the Planetarium Astronomer. James has been doing that for a while. Also the University of Houston is an adjunct professor. For those that come out to the Jorders, they know James because James is out there quite a bit giving talks and also night sky laser tours. So tonight's talk is going to be about the secret life of stars, and we're not talking about Hollywood stars. we lost a great one here the other day, but James, go ahead and take it forward.
Okay. Make sure everyone can hear me okay. The microphone seems to work. And yeah. See if I can this works. Okay, oops, I went the wrong way. Secret lives of real stars. And by demand, I'm going to use the HR diagram kind of as my guide. That way, this is an adaptation of several lectures I give at U of H downtown to students who are non-science majors, like business majors or art majors, political science majors. That's the level this instruction will be at. If you're more of an expert than that, then just kind of hang on well. So we see the HR diagram, and the challenge students have in reading this diagram is that's not a normal graph. First of all, look at the y-axis. Notice how the scale is not linear. But every time I show this to students, I make sure they read the graph carefully and observe how it's not a normal XY graph. Also, the x-axis is nonlinear. Not only that, it goes the wrong way. Most students assume that the quantity on the x-axis will get bigger as you go to the right. But that's not what's happening here. This diagram graphs luminosity or intrinsic brightness against temperature. And of course, astronomers have this nice acronym at the bottom to indicate the temperature by letter. Of course, originally, I think it was Swan-Leavitt put them in order by how big the hydrogen line was in the spectrum. Then they realized, oh wait, temperature is more important. So they combined categories and reordered them. That's why they're not in alphabetical order anymore. And so you can see how the temperature roughly corresponds to a color that we would see. And by the way, these colors are more traditional. The real colors of stars are really blue, white, or red. It's hard to get any color in between because you have the maximum in the ultraviolet, and so you have blue and almost no red, or you have the maximum in infrared, and you have red and almost no blue, or you just have white. It's hard to get a peak in the middle of the spectrum without including all the other colors too. But by tradition, we say the G stars are yellow and K stars are orange, but really it's blue, light blue, white, pinkish, and red. Now, if you want a graph that behaves like a normal graph, what you can do is take the brightness in one color, subtract the brightness in the other color, and that will make these positive numbers, oops, over here, and these somewhat negative over there. And that's sometimes, some graphs are like that because that graphs directly observed quantities. That's something that astronomers like to do a lot. But that's the typical graph. You can see where some of the stars are, but if you were to graph an entire nebula, say, you'd find there's a main sequence that appears. And so it's called the main sequence as a result. Over 90% of the stars are on this main sequence. There are also luminosity classes, along with the spectral letters from hottest to coolest. And by the way, the acronym is Oh, be a fine girl, oh guy, whichever one you want, kiss me. Within each category, we have luminosity classes. So this is the main sequence. This is the subgiants, 3 and 4. And these 3 is giants, and 1 and 2 will be super giants. So our sun will become a giant, but not a super giant. And there's also a 0 category here as hypergiants. And we can tell them apart by spectra because the supergiants do have narrower spectral lines than the main sequence stars. I put this in so you can see that we all call our sun average because it's right dab in the middle of the program of the graph. But it's kind of a misleading statement. Because you look at how many stars there are, over about 80% of the stars are M dwarfs. In other words, 80% of the stars would be like right in here on the HR diagram. And that's because they're smaller and easier to make. And also look how long they shine. They shine for, that's 200 billion. This is in millions of years. Our sun, 10 billion years. K stars, 50 billion years. M stars, 200 billion years. Amen. How long the whole universe has been around? Yeah, the 13.8 billion years. That's not enough time for these to burn out, which means all of these stars that have ever formed in the universe are still around. Same thing with these. But these other stars, like this one, these shine for only 10 million years. 100 million years. That's 1 billion, 3 billion. These ages are all less than the universe's age, which means there's been time for them to burn out. So there aren't as many of those. First of all, they're bigger. You need more mass to make them. They're hard to make, and they don't last as long. Thus, by distribution, and by the way, some of these smaller M stars can last trillions of years. So again, this is nonlinear. So we get to the end of M, you're in the trillions of years for the stars to shine. 80% of stars are this, 8% like this. And so 88% of the stars are smaller than the sun and cooler than the sun. Our sun's in the middle of the diagram. It's not quite average, per se. There are stars bigger than the sun, but they aren't the majority of stars, a vast minority of stars. Only 2.7%, actually make that 7.7%, maybe 8.1%. About 8% of the stars are smaller than the sun. Yeah. Actually, no, we do this again. 88 plus 5 is 90% of the stars are smaller than the sun. And only about 3% of the stars are bigger. Yeah, add all this together. The thing is, though, the stars we see in the sky aren't going to be these. These aren't bright enough to be seen unless they're right next to our sun. So all the stars you see in the sky are going to be stars like this, this, or this. That's another. All the most numerous stuff we can't see.
Question,
Yes.
before we get off this chart, the big guy on the left, okay? You show mass of 50 solar masses.
Yeah. Yes.
Up at the top there,
Oh, yes.
it says 50 solar masses. Oh, that's for main sequence,
Main sequence stars.
an O-type star.
O-type star in the main sequence.
Okay, so that's not a giant
It's going to be.
star.
It's going to become, yes, right. The giant stars are here. These are O stars on the main sequence.
But then under giant star, you have a mass of only the maximum of 5 solar masses? The mass?
Mass, yeah, radius mass, yes.
That's a giant star, 5 solar masses? Seems not that.
Yeah. 1 to 5 solar masses.
1 to 5.
Yeah.
Okay.
So our sun will become a giant, but won't ever get in the league of the bigger stars, like of the O stars. This is the M star, and we can't see it naked eye.
Yes.
You can see Alpha Centauri, which is another G star, like our sun. Sirius, by the way, is an A star on the main sequence. And so, by the way, if you go back to this, you'll find that when you look at the type of the star, it's going to have something like G2V, and the G. And by the way, these are subdivided G0, 1, 2, 3, 4, 5, 7, 8, 9. Each one of them is, and the V will be the 5. So the main sequence star. If it's a giant, it will say something like A3, 2, Roman numeral 2, and so on. And that's how we mark them.
One other question.
Yes.
On the HR diagram that you showed previously versus the opening HR diagram, what's the difference? I
Oh,
mean, go
this
back
one
one slide. That's the standard line,
yes.
but prior to that, you showed another chart here. What's the difference?
Well,
between
this
the-
is just some famous stars.
Oh, this
Yeah.
is it.
And you'll see that most of the ones we see naked eye tend to be the giants. Those tend to be bright enough to shine all the way to us from far away. And so I was just making sure that you understand that most of the stars are too dim to be seen naked eye, including several ones like Barnard star. They're very close to our sun. We can't see them naked eye. And by the way, the mass of the star, the initial mass when it first forms, determines where it is in the main sequence. One more thing, we talk about stars moving on the main sequence. This is not movement in space. This is changing luminosity and temperature. So moving on the HR diagram, I have to make sure I say this like 10 times to my students, is not how the star moves in space. It's about how it gets brighter or dimmer or hotter or cool. And stars can't move along the main sequence because once they're here, that's a stable state that lasts for the most of the lifetime of the star. But once our sun gets to there, it stays there for 10 billion years, which means luminosity and temperature are stable for 10 billion years. So this,
Why is that? Because of the size of the thing?
yes, because there are two forces in balance, and we'll get to that later on. And so once the star is on the main sequence, that's the most stable will ever be, and will remain in that position for its lifetime. Now, these stars aren't there, for only millions of years, but these hundreds of billions of years, even trillions of years. This chart shows how long each star spins, a star like our sun would spin in each stage. So our sun's the main sequence star for 10 billion years, but the initial stages, the interstellar cloud, the cloud fragments, and the protostar stages are way shorter. So I have us focus on the first column. You can see that this is the most stable stage. That's why it lasts the longest. And these are orders of magnitude shorter than the 10 billion years. The stars is an interstellar cloud, which is clumpy. Why is it clumpy? Well, think of the dust under your bed. Is that a smooth layer of dust, or are there dust bunnies in it? Now, how did the dust bunnies happen? Did somebody go down there and make them? So you see that unless you have someone smoothing everything out, gas and dust will be clumpy. And under gravity, once you have enough mass in one spot, it becomes a runaway process. And thus the cloud fragments, and then you have what's called a protostar, and then it moves toward the main sequence. That is, the temperature and the luminosity shift toward a stable state, and you have a main sequence star which lasts about 10 billion years if it's the sun. And by the way, the interstellar cloud is orders of magnitude bigger than the solar system is. Once you have a protostar, you can plot it on the diagram. You can plot its luminosity versus its temperature. Of course, it hasn't begun nuclear fusion yet, therefore it's cooler, so it's to the right. But it's also much bigger, more luminous because it's bigger. Keep in mind that the luminosity is related to the surface area of a star, and the surface area is related of a sphere is 4 pi times the radius squared. Thus, a much bigger thing is going to be more luminous than a smaller thing, even if it's not as hot. So then as it goes to those stages, it goes to the main sequence. It gets cooler, then gets hotter. The track where it's getting cooler is called the Hayashi track, and when it's getting hotter, it's called the Henye track. And by the way, the Henye track begins once the radiative zone of the star forms. If you're not sure what the radiative zone is, I included a diagram of the sun's layers. The sun has the core where nuclear fusion occurs, has a radiative zone and the convective zone. Here, the warmer gas rises and cooler gas falls. And so it's just, once the radiative zone forms, it becomes hotter, and thus that means that the Star shifts to the left on the HR diagram. That's what getting hotter means, until it winds up on the main sequence. Other main sequence stars have similar tracks, but they wind up in different spaces on the HR diagram. Note that the less massive stars have a shorter Hennier track because they form a smaller radiative zone. And the smaller stars go straight down because they never form a radiative zone. They are fully 100% convective. Whereas the more massive stars have a longer Hennier track. In fact, the ones up here just go straight over. They have a short Hayashi track and a long Hennier track, which means they just get hotter, ring about as luminous. And by the way, the protostars that wind up as stars F through M, so that winds up here to here, those are called T Tauri stars. And the ones that wind up as A or B, those protostars are called the Herbig AE or BE stars. And the difference is that these stars are so hot that there's much more lithium destroyed in the interior. That's how you tell optically or by spectrum. O stars are already on the main sequence by the time we see them, by the time they clear the dust. And therefore there's no protostar that's going to be an O star. Because they go to the main sequence so fast that by the time we see them, they're already there. So any protostar will be either Herbig, A or B, or T Tauri, F through M. Yes.
T Tauri, or is it Tauri name because?
The T Tauri is the example star.
Okay.
T Tauri, yeah. Taurus, yes. T Tauri is a star in Taurus. And by the way, if you're confused about star names, the Greeks did Alpha through Omega. And then we went back and did letters, A through Z, when you ran, because there are more than 24 stars in a constellation. And then we have two letters, like RR or TA or something like that. So T is a star in Taurus. And then we found out there's one of these protostars.
The T Tauri must be variable, right?
Yes.
What I remember is they started variables in R because no constellation name, that were being used were up to R.
Yes. Yeah. R, then S, then T, yeah. And then
That's background to getting it out. Double letter.
so the main sequence is equilibrium because all the mass of the star falls into the middle. At the same time, there's pressure, thermal pressure, driving mass out. And so both forces are at work. The net force is zero, the star is stable. So you see, if any of the forces were not there, let's say the star were to run out of fuel in the core, and there would be less thermal pressure, and then you see what will happen to the star. Under gravity, all the mass would fall to the center. But while the stars are in the main sequence, there's nuclear fusion going on in here, and that creates a thermal pressure force that drives the mass out. At the same time, under gravity, all the mass is falling in to the center. Net force, zero, stable star. And by the way, our sun is about halfway through, 5 billion years into its main sequence cycle, has about 5 billion left. So we all worried about Y2K, but really Y5B is the much bigger part. This is, by the way, is the proton-proton chain. That's what stars like our sun use to make helium out of hydrogen. By the way, the proton is just a hydrogen ion. And make these, of course, you do this twice. So you're using 1, 2, 3, 4 protons to make a helium and 2 protons. The other sequence that goes on in stars is called the C&O cycle. Yes, the heavy elements are already there because these aren't first generation stars. They're there in trace amounts. But the temperature must exceed 17 million Kelvin in the core for that to become dominant. Our sun's temperature is 15.7 million Kelvin. So the sun does a little bit of this, but it's mostly the proton-proton chain, of which the sun is making hydrogen into helium. And by the way, if we were using English instead of Greek for element names, helium would be sun stuff. That's literally what it is. Because the Greek, they found it in the sun. They found this in solar spectra, how they discovered the element. But they didn't want to say sun stuff. That doesn't sound very scientific. So they said it in Greek, but that's what it is. This diagram just shows how inside the core during this 10 billion years, the sun's core is changing from mostly hydrogen to mostly helium. There's always some helium there because helium is primordial like hydrogen. The primordial elements in the universe are about 3/4 hydrogen, 1/4 helium. That's what's formed in the Big Bang. That's what's in the universe. But in the sun's core, the hydrogen gradually changed to helium. That's called hydrogen burning. But then at some point, when you're making something right, at some point you're done. Because the conditions that favor making hydrogen to helium prevail only in the core, not in the rest of the sun. So at some point, the hydrogen that's in the core where it's hot enough is going to be made to helium. And then what happens next? Question?
Yeah, according to the diagram that you just had up there, after 5 billion years, our core is about half helium.
Yeah.
According to that.
Yeah, and it's been 5 billion years.
Roger.
So these are the stages after main sequence. Again, observe how we're on the main sequence 10 billion years. With the other stages, we're going to talk about are way shorter, exponentially shorter, orders of magnitude shorter than just our main sequence stage. So it goes on the subgiant branch, helium flash, horizontal branch, asymptotic giant branch, then a planetary nebula, white dwarf, and black dwarf. So the main sequence stars can't fuse helium. They're not hot enough in the core. Thus, when they make helium, helium just accumulates in the core and you can't do anything with it. So as the core fuels the helium, only the part in the core that's not the helium can burn. As these burning shells get smaller and smaller, you'll find the star gets hotter and helium gas always expands. It expands and cools off. So how do you draw expanding and cooling off on the HR diagram? Well, it goes up and to the right. It just means that as the star begins to burn most of its hydrogen into helium, it's going to be hotter, it's going to expand and cool off. Therefore, it will be cooler, that is redder, but also much more luminous because it's a bigger surface area. And that's how we draw that on the HR diagram. Now, once the temperature rises to 100 million Kelvin, you can burn helium. So that's why the sun can't burn helium right now. It's just not hot enough inside. Now, burning helium takes this process, oops, right here, but this is not normal beryllium. Normal beryllium is, the stable beryllium is beryllium-9. If you look at the periodic table, you see that the atomic mass of beryllium is 9. But this process makes beryllium-8, which will last 8 times 10 to the minus 17th seconds, unless this happens before in that time. And that's why you need these high temperatures. Well, the same thing with we need very high temperatures to have fusion in the first place because protons will repel each other. But under high temperatures, they have high momentum. They're moving around very fast, and that can overcome that repulsion. So you have to have very high temperatures, everything moving around at incredible speeds. That's what temperature is, by the way, the kinetic energy of the particles in the gas.
Hey, Jay?
Yes?
I have a question for you.
Yes.
So if that second reaction doesn't occur and the beryllium decays, we know what it decays into.
I'd have to look that up. I forget. But basically, for this purposes, this reaction can occur. And thus, I imagine some individual beryllium 8s do decay, although some of them get happen first.
You know, I was wondering if it decays, then does it participate in some other sort of heat change?
Yeah. Now, I think it would decay into something, will probably decay back into its components, the two alpha particles. Yeah. And so so this would happen, and then you go back here. So you have to have these high temperatures so that you can get them slamming into each other in this much time so you can get the carbon.
I know there's some residence or something that makes that reaction able to happen at all.
Yeah.
Without this weird coincidence of energy levels, everything would just get stuck. In helium.
So you have, by the way, this is sudden because our sun can't fuse helium, and helium is under a lot of pressure, which means it becomes degenerate. It becomes so compact, it's held up only by the quantum mechanics rule that electrons can't be in the same state. It's possible to compress matter so much that any further compression would force electrons into the same state, and you can't do that. So there's a force that stops it right there. And so the temperature builds up, and it starts suddenly. It's called the helium flash for that reason. Although you won't see the flash because the rest of the layers of the star absorb the energy. But it means this helium fusion begins rapidly, and then it reaches another stable state at state 10, and what's called a horizontal branch. And just like the main sequence, stars won't move along the horizontal branch. This is just a graph of the luminosity that these stars have. Different types of stars will wind up here or here or here or here. But they will stay there for, in our sun's case, 50 million years. That's way less, of course, than the 10 billion years on the main sequence. Then, of course, same thing happens, right? You're fusing the high helium into carbon, but the sun can't fuse carbon, and it never will. It would have to reach several hundred, not just 100 million Kelvin, but several hundred million Kelvin, 500 million Kelvin to fuse carbon. And our sun won't ever do that. You need more mass, more pressure to reach temperatures like that. And bigger stars will do that, but our sun can't, ever. So the carbon builds up here. So all the burning happens in these two layers. This is the rest of the core where helium is burning into carbon. This is the carbon that's been made and it's filling up. Nothing's happened to it. Yes.
It's hot over there. The pressure's tremendous over there.
Yes.
The carbon is in the middle, but it's called ash because it's just not hot. And
It's called ash because the temperatures here are not enough to burn it.
I'd say again.
The temperatures are less than 500 million Kelvin.
So it can't burn.
It can't burn yet.
Roger. Thank you.
Yeah, it's just not hot enough. It's hot. I wouldn't recommend going there. But it's not hot enough to burn carbon. And it never will be for a star like our sun. So this is just going to stay here like this. And now you have two burning shells.
So then that star then
It becomes a red,
star?
yeah, it becomes a giant again. The same thing that happened when the helium core was filling up. Same thing happens again. It becomes bigger and cooler because the gas expands and cools off. And you have, this is the asymptotic giant branch. It lasts about 10,000 years. Again, that's way longer than a human lifetime. So we can't notice that we can't observe these happen for any one star. We have to observe this star doing one thing and that star doing the other thing and put the whole thing together. The thing is, though, when you have this part, the helium is burning into carbon, so this is filling up with carbon. When there's almost no helium left, this burning takes over, the hydrogen burning into helium. Then it's made enough helium to burn helium into carbon again. And then that is used up, and so it goes back to this. And then you've made some more helium, now you can burn into carbon, and so on. Every time that happens, there's a thermal pulse that expels the mass, some of the mass of the star. And stars, these giant stars can lose up to 50 to 70% of their mass that way.
How much is that, James?
50 to 70% of their mass. which is most of their mass. And that's how you get a planetary nebula. This is the mass of the star that was expelled in those thermal pulses, leaving only the core, a carbon core. A planetary nebula with a white dwarf in the middle. By the way, the name planetary nebula is a mistake. Nobody corrected. Just like Columbus calling people Indians. This is not India, but the name stuck. This kind of looked like a planet. When they first saw it in the telescopes, they called it a planetary nebula, and they realized it has nothing to do with planets, but the name stuck anyway. Because if you change it, you have to go back and change all the literature.
We can't do that.
And we can't do that, yeah.
So the white dwarf in the middle?
Yeah.
Is
It's
a
called the-
carbon star?
Yes, and is made of carbon. Now, what they call carbon stars, those tend to be asymptotic giants. What happens when you have these thermal pulses, you can dredge up material from the core. And sometimes some of this carbon can get dredged up. And so these asymptotic giant branch stars, some of them are carbon stars. Because the carbon of the core has been dredged up in this process.
Wolf-Rayet star?
Yeah, Wolf-Rayet stars are different. Those are much hotter stars. Yeah. So here is the planetary nebula that can result, and they can take various types of forms. And by the way, so everyone knows, this is something like this seen sideways. Did everybody see? If you saw this pole on, it would look like that, right? Okay. But ultraviolet light given off by the white dwarf is causing the gas and dust that was once part of the star to glow. And our sun will do that in about 5 billion years. It's too small to blow up. So even here in Texas, bigger isn't always better. The bigger they are, the harder they fall. But it will do this. And this, by the way, is expanding. It's a picture. It looks still, but it's not still. It's expanding into space until it dissipates. And also, remember the UV light is causing it to glow. But this white dwarf is not generating any more heat. Oops. Therefore, it's just cooling off. It's very hot right now, thousands of degrees hot, but it's just going to cool off, which means that at some point it's too cool to emit ultraviolet light in much quantity. And that means that this will stop shining. So the planetary nebula around the white dwarf disappears. For one thing, it's spreading out into space, but more importantly, the star can become still a white dwarf, but too cool to shine brightly in the ultraviolet. And with no ultraviolet light, nothing can make this glow, and this will stop being visible. That's how we draw that on the HR diagram. So you have this, it expels mass, still luminous, and then it comes just a white dwarf without the planetary nebula, because as they become too cool to shine brightly in the ultraviolet. Of course, it keeps cooling off. It becomes a black dwarf. Look how much time it takes to become a black dwarf. So are there any black dwarfs yet? No. A black dwarf is a theoretical construct. We imagine that this must be a black dwarf at some point because it has to cool all the way off. There's nothing in the core of the white dwarf generating any heat. Therefore, based on laws of physics, it must just cool off to the temperature of the space around it. And by the time it gets to 3 Kelvin, equal with the space around it, it won't shine visibly at all. It'll be a black dwarf.
Ball of carbon.
Yeah. It's like a hunk of coal in space. So you can't get the dwarfs confused. A brown dwarf is something that wasn't massive enough to form a star in the first place. Then you have a white dwarf. Then you have a black dwarf. And so there's also a happy and grumpy and the Gimli and the okay.
So all those identifications.
Yeah.
Were in the 9 billion,
Yes.
in the 12 trillion,
Yes.
in the 15 is a quadrillion.
1 quadrillion years to make a. Yes, right. So you're saying that this is 1 quadrillion years. In fact, I like to write these numbers out for my students. It's kind of tedious here, but I get a number like this to make my students appreciate how big a number is. I write it out on the board. 1,000, comma. Oh, that's a big number. It's more than national debt. Yeah. An example of a white dwarf that's very famous and popular, it would be Sirius B. It may have been a star about 5 times mass of the sun, composed of carbon and oxygen now. But here is Sirius B next to the, of course, Sirius A, which is the brightest star we ever see at night. We can use this information we learned to estimate the ages of globular clusters. That's an old globular cluster. We can see it over here because there are no blue stars at all. But you can look at it here as well. You can see that there are no blue stars on the main sequence. These stragglers are there probably because stars in the core of the cluster collided with each other or interacted with each other and exchanged mass, making some of them more massive. But as in general, if you see that there are no blue stars in the main sequence, it's an old cluster. A young cluster would have stars all in the main sequence all the way up to here, and no giants, no white dwarfs. So you can plot stars on the HR diagram and estimate the age of a cluster by noticing where the stars turn off the main sequence. Because there's been enough time for all these to evolve away, but of course not enough time for stars like our sun to evolve away.
One stupid question.
Yes.
How, for a globular cluster, how do you determine the surface temperature of a given star in that?
We can probably aim a spectrum. We have enough resolution to look at each individual star. And all you need is the temperature, and the luminosity will be the intrinsic brightness, which you can gain by estimating by looking at the spectrum, looking at there's a relation between mass and luminosity, a relation between temperature, and if most stars are on the main sequence, you can get the temperature, you have an estimate of luminosity as well. By the way, low mass stars can't become red giants. And so they're fully convective. The helium does not accumulate at the core. Remember that in our sun, the helium built up at the core. But if the star is fully convective, then nothing builds up at the core. And so these very tiny red dwarfs won't become giants. So what they will do is basically just start here and they just do this, which means they will just get hotter, becoming blue dwarfs and ending as white dwarfs. Now, what about stars more massive than the sun? By the way, these stars begin to burn helium before it becomes degenerate, which means before it becomes compacted so that only quantum mechanics holds it up. That means there's no sharp turn. Oops. There is instead this right here. So instead of doing this and doing a sharp turn over here, these stars do this. And it's called a blue loop, by the way, where they briefly get hotter and then return to the giant strap. Note that the star doesn't necessarily become blue. It just gets bluer. So like a red shift doesn't mean turning red, it means shifting toward the red. The same thing with a blue shift, doesn't necessarily turn blue, it just shifts toward the blue. So stars at least 2.5 times as mass as the sun will burn helium gradually and not suddenly like stars like our sun, because the helium won't become degenerate first. This area is called the instability strip. As these giant stars are in this area, at these temperatures and luminosities, they begin to pulsate through the twice ionized helium, or basically alpha particles. Because the star becomes more or less opaque, which means brighter or dimmer. It expands and then cools off, then collapses again, expands, and so on. And because The mass of the star determines how far it can expand before it collapses. The period of the star is related to its mass, which is related to its intrinsic brightness. Thus, these are very good, what are called standard candles. We know how bright they're supposed to be. The key is that our sun won't ever get over here. So you need stars more massive than the sun to become these Cepheid variables or Lowry variables. So remember what our sun did up to carbon? More massive stars can fuse carbon into other things. And so you have many more elements formed in here. The most massive thing any star can make is iron. To make anything heavier than iron, you have to put energy in. Making everything up to iron gives off energy. But making iron into anything heavier than that requires energy to be put in. And thus, iron is the heaviest thing that can be made by nuclear fusion. And so these more massive stars to make everything, they can make carbon into neon, then magnesium and silicon. And by the way, they're in each time they're adding helium nuclei. That's why you're skipping over some of the other ones. So you're skipping over things like fluorine because you're adding a helium nucleus every time. Then iron becomes iron ash because it can't fuse. And then once the process stops with too much iron in the core, then the thermal pressure is gone, which means that under gravity, all the mass falls into what, the middle? Now there's so much mass here falling so fast that the protons capture the electrons and become neutrons. So you have a neutron core that squishes down until quantum mechanics stops it again. The other material lands on the core and bounces back out, tearing a star all the way apart. That's a supernova, which our sun won't do. It's not massive enough. And thus these neutron stars, by the way, they form at about 1 trillion Kelvin. Then they cool to maybe about 1 million Kelvin very quickly. But I can't graph down here. You see that? So HR diagrams don't only graph neutron stars or black holes. They don't fit in that space. So once these massive stars blow up, they just go off the diagram. That's a little bit overview of the lifestyles of the real stars. I'm gonna pause here. Does anybody have any questions? Yes, go ahead.
When the outer atmosphere of the star is up down like that, what does that do to the planets?
Well, nothing nice, unless you're a far away planet. Basically, the sun will swallow the inner planets when it comes to red giant. But that means that if we move to Europa by then, maybe it'll be nice and warmer. The ice will melt and maybe kind of oceans there. But anyone on Earth in 5 billion years will not be having a good day. If it doesn't reach the Earth, it will certainly scorch the Earth dry and kill everything, even the cockroaches. No question? Yes.
Well, not exactly a question. We've had telescopes for about 400 some. I mean, I've been hearing pieces of this all my life,
Yeah.
and I'm old, so a long time. And we've had telescopes 400 years, learned a lot with them. We've had spectroscopy for 150 years or something like that. I don't know exactly when, maybe 200 years, I'm not sure. And so all the rest, so we get a lot from the telescopes and spectroscopy, but all the rest is just physics theory, right? Physics tells us how these things work.
Yes.
And that's what it is. Telescopes, spectroscopy, and physics theory gives us
Exactly. Yes.
everything you took. Okay, good.
And of course, now we can get above the atmosphere so we can observe in other wavelengths to verify some of this as well. You remember that our atmosphere is opaque to all electromagnetic light except visible light and radio waves. Therefore, the only astronomy you can do on the ground is visible astronomy with a telescope or radio astronomy. All other astronomy must be done in space.
So the end of the red dwarf's life, it becomes a white dwarf.
Yes.
Is there any planetary nebula there? It just transforms?
It gets hotter and then this process stops.
That's never been observed.
It's never been observed because it takes Remember, they shine for 200 billion years. Some of them shine for even longer, trillions of years. And so, again, that's purely theoretical. We can't, there's not been enough time in the universe for any red dwarf to do that.
So if we ever leave the Earth because, you know, we're on a time clock.
Yeah.
Well, we need to find a red dwarf.
But the thing is, red dwarfs are tricky because they're habitable, they're very volatile, and their habitable zone is so close that any planet in that zone will probably be tightly locked, which means the average
没
temperature
呢，
will
还
be
早
right,
呢。
but the real temperature would
Ah.
be, but the real temperature would be not right, because the real temperature you experience will be either too hot or too cold. Up and down. Or if it's tightly locked, it will be either just all way too hot or all way too cold. So you need to have what? Yeah,
And we'll learn stars. too.
yeah. A lot more flare stars, exactly. So they're much more active. Many of them are much more active, and you have to be much closer to them. So close that your planet will be tightly locked, probably, which will mean that although the average temperature of the planet is just right, the temperature you really experience is not.
Unless you're on that. fringe
Unless you're
of-
on the Terminator. But living just from a Terminator world, I'm not sure you can get 8 billion people to do that.
Right.
Other questions? Yes.
It's actually something, the lead article of this month's issue of Science Telescope is sort of complimentary to your talk.
Mhm.
The question that it asks is, how big can stars get?
Oh.
And it talks about the research that's been done in determining how big are the largest stars. So I found that to be useful.
Yeah.
Again, it competes very well.
Yeah. And of course, the very large stars would be the supergiants, even the hypergiants. Those are stars that begin at O on the main sequence, and they go from there. And they shine for millions of years. If they're early enough in O, probably less than maybe 1 million years, which is a long time, but not long enough to have anything interesting happen. So think of how long it took Earth to form and how long it took life to begin on the Earth. If our sun were shining for only 10 million years, it wouldn't have happened.
So the stars can only make iron, but then when the supernova occurs, that's what the other element.
It's a supernova and other processes. I didn't look into that. I didn't prepare that information for this talk. But that makes some of the elements. And then
Planetarium Astronomer also makes some, I've heard
Yeah.
that they also make heavier elements.
yeah, I think that would be a whole different talk actually. But I didn't prepare that information for this talk. Yeah, but you're right. The explosion.
Stars only make iron except the.
Yeah,
random byproducts.
But we have gold and silver and copper and things heavier than iron, lead. Those things exist. They're made somewhere. Supernovas make some of them, but there are other processes that make the elements as well, the heavy elements. The stars make only iron, then it stops. And our sun makes up to carbon and stops. And some of them have oxygen too. Other questions? Any questions online?
Put them in the chat.
Oh,
Okay.
there you go. I'm gonna hand this over to Lee.